So for the grad students here, among other things, not only I am late, but when I was in a rush trying to get my hard drive, I left behind, I prepared a sheet. For the grad students, we need to assign projects for you. And with 2 of you, I already talked, but there are about 9 left. So this Friday, tomorrow, I'm going to make myself available. And I would like to meet with 15 minutes with each grad student. Not you, because we already met. Not you, but there are many others. And I just want to get a sense of what do you like, what's your research. The project is still going to be closely tied to the fundamentals you learn in the class. But if we give it a spin that is good for your thesis or things that get you excited, everybody is happier, right? So tomorrow from 10:30 until noon, and then from 1 until late in the day, if you guys want to sign your name, like I asked Daniel to prepare this sheet, so I know what to expect. If for whatever reason you cannot make it on Friday, let me know. But if you can make it tomorrow, good, we get done with that. All right, and you can get started earlier. You might need to learn some of the material I'll teach later. But grad students are good, so it shouldn't be a problem. And it should be an awesome thing. Very often, those things are really good hooks for future employment. Because you say, I did this. Oh, I cannot believe you did that. Oh, yeah, sure I did. So, all right. The TAs also, I don't know if their email already went out, but we have two seminars rescheduled for Tuesdays, right? So those in Kemi and Mari can go to the DBR seminar. And the proper date for the exam, which is not on Thanksgiving Day. So if the email hasn't been out already, it will go. This is only for grad students, huh? But
yeah, if yours, yeah.
He just looks young. All right. So I think now things are established. We had a few people adding the class as the weeks went on, so somebody's putting a good word for us for now. So it's good. So, okay, we were talking about the whole universe of putting two things together, from screws to Elmer's glue, right? We talked many things, of which welding is a tiny thing, and from welding, using an arc for welding is even tinier. And from using an arc for welding, there were many types. We talked about TIG, we talked about MIG. Remember, I showed you a million acronyms on the first class, and I knew it would make no sense to you then, but by now I say TIG and MIG, and you know what I'm talking about. At least it doesn't strike you as coming out of nowhere, right? And we started with non-consumable electrode, right? If this non-consumable electrode, can it be autogenous? Weld? Yes, because autogenous means, autogenous is like, auto means self in Greek, right? And we speak Greek, I guess. But so it means no filler metal. You're just remelting the base metal. So take, for example, plasma. You will see demos of that. I don't remember if it is either today or next week. You will see those demos. Then we said, okay, what if we do melt the electrode, right? And that's the case of MIG, right? But we said the protection is never with these chemical reactives that are called fluxes, right? It's just with a shielding gas or something like that. If I do MIG with the official name, gas metal arc welding, can I make an autogenous weld? No, of course not, because I'm putting something in there, right? The something might be very similar, which we would call homogeneous weld, right? Can be different, which we would call heterogeneous, but is not going to be autogenous. For whatever it's worth, sometimes it matters. And then we moved on and said, okay, fine. We have an arc, like TIG, but we're melting the electrode, like MIG, and we're protecting it with fluxes, right? And it's something that is new. And if it is fluxes, we talked about flux core, right? That we use the same machine as MIG. It looks everything the same as MIG, except you can get away without putting a gas, right? And you would have a good protection for the melt. And then we said, okay, there's something else similar to MIG and similar to flux core, that is submerged arc welding. So is submerged arc welding done underwater? Oh, I see hesitation. No, it's submerged because it's submerged under fluxes, all this bed of fluxes. And I didn't get to show you some videos, but I'll show those to you today. So looks like MIG in many aspects. You have a solid wire, right? You have the weld pool, the weld here, right? It looks like flux core 2, in which the melt is protected by fluxes, right? Flux core is always a tubular wire. Subarc welding can be tubular, might not be, right? So this here is just powders. And you will see all this in action. So this drawing, which is of my authorship, is somewhat artistic, but you're going to get to see the reality, right? And it's like flux core in the fluxes. The wire here can be many things, as long as we protect it with the fluxes. Now, the fluxes we can mix with metals, and we can make alloys. So we can make crazy stuff with this process. So I mentioned to you something about how, since the fluxes have chemical reactions with the metal, you can add oxygen, you can take oxygen away, or phosphorus or sulfur, a bunch of things. So there's this term called basicity. I mentioned briefly to you that is like a legacy from the steel-making industry, in which they, depending on the chemical composition of the fluxes, they call it acidic or basic, but it has nothing to do with pH. I don't know why they call it like that. I asked. Nobody gives me a straight answer. Yeah?
It's just because it makes the ratios easier. It's just ratios. They just called it that because the ratios.
Yeah, but if it is just ratios, there are so many other ways to call it too, right? It's true. It's because of the ratios of different types of fluxes. Why acidic and basic beats me. But they're called that way. There's nothing to do with pH. Nothing to do with pH. Something else is called neutrality. That means if you're going to have more, you're going to change your manganese and silicon content in your alloy. Now, as a preview, manganese and silicon are special because manganese and silicon are very reactive with oxygen. So if you have a plate that is rusty, you can weld on it without problem if you have an alloy that has high manganese and high silicon. Now you might say, why would anybody want to weld on a rusty plate? Well, the answer is everybody wants to weld on a rusty plate because it means you can store it outside and you save money without having a shed, and you can weld it without having to clean it. That saves time and money. So as we talked many times about welding, everything you want to do, you can. But often you don't want to do it, right? Do you want to have an awesome weld? Sure. Do you want to build a new shed and clean every weld you do? Nobody wants to do that. So in steel welding, you get away with you have higher amounts of manganese and silicon, and that sucks up the oxide, right? But you play a funny game. For example, let's say a plate is oxidized. I weld it, first pass, right? I sucked up all the oxygen and everything. Okay. Now let's say I keep welding. Now it's clean. Now I have too much manganese and too much silicon, and my weld will be, for those of you in MATI, you know, is more hardenable. So my weld is going to end up being super hard. Same as if you say, well, I don't know if my plate is going to be rusty or not. I'm going to get an alloy with high silicon and manganese. Sure. And then your weld is super hard, and you have issues of cracking and fracture and poor toughness, right? All these decisions are decisions that are made on commercial products. I'm explaining you the fundamentals, but some guy from many of the suppliers of welding consumables will say, buy this brand and this model, or this brand and this model. It's all marketing. It all comes down to this type of thing, right? You can add alloying elements. For example, imagine you have a steel plate, but you want to make an overlay that is very high in chromium and carbon, such that it gets chromium carbides and is very wear resistant. You can do it with submerged arc welding because in addition of putting just the ceramic powders, you can put, for example, before the ceramic powders, all these high chromium and high carbon powders that will be molten and will give you this super wear-resistant alloy, right? You can play so many games. as long as you know what you're doing. Filler material is automatic wire feed, whether it's solid or metal core. Polarity, and this is where we stopped last time, typically it's electrode positive. Which other process can you tell me that runs in electrode positive? MIG. MIG is typically electrode positive. How about TIG? No. Yeah, the TIG is negative. And like everything I ever tell you, I promise you there will be an exception. But for the most part, you run TIG in negative and MIG in positive, right? But you can use waveforms and, for example, have sometimes the electrode positive and sometimes negative. Right now, it doesn't mean much to you, but you're going to see that this is extremely important, and you will know why it's important and how to go about it. You can run it in constant voltage. Who runs in constant voltage, MIG or TIG? Oh, yeah. So in TIG, right, especially when you do it manually, you keep the constant current, so you always have the same intensity of the arc, right? But the electrode is this tungsten that is non-consumable, so it's always in the same place, and you're a happy person. Now, in MIG, you're melting the wire, so typically you want to have constant voltage, so the arc is always the same length, and you're not like having crazy problems with arc length as you're feeding the wire. Now, in submerged arc welding, when you're running at high currents, you might want to do something that is not done in MIG, that is you run at constant current. But it's tricky because they say constant current, but means also constant voltage. And this is funny because voltage and current are related through the resistance or impedance of the system. So in this case, by adjusting the wire feed speed, you're adjusting the impedance of the system, right? So you have to always leave a variable of adjustment, right? Whatever you set up in your machine, the system has to accommodate to it. In MIG, you accommodate the voltage, and we'll give you a current. In TIG, you accommodate the current, we'll give you voltage. But in subarc welding, you put the voltage and the current, and then something needs to adjust, and it's the wire feed speed. All right, so subarc welding is, remember I said like TIG is like a scalpel, MIG is like a knife. This is like a chainsaw, right? So it depends on what you want to do. Do you want to do brain surgery or you want to chop down a tree? You don't use the same, right? This is for chopping down trees, right? You want to make enormous plates, you want to weld a ship, you want to weld a bridge. Subarc welding is the way to go. TIG, no. TIG is you want to make a race car, right? Very different type of things, although both are based on arcs, right? The only one that can make bigger welds than subarc welding is electrogas welding or electroslag welding. Why do you think I cannot make a weld? Why do you think electrogas welding, which you know what it is, can be why do you think this can be bigger than subarc welding? Why? Why can electrogas welding be bigger than subarc welding? Do you remember electrogas welding, more or less? Used to weld ships. Like subarc welding is also used to weld ships. In electrogas welding, do you remember how we went? Like we would put like these copper shoes and move up, right? And it's like a swimming pool of molten metal. So why subarc welding cannot be as big?
The current is high for electrogas welding?
The current is higher for electrogas welding, it's true. But again, I want to go to the laws of nature. What you said is true, but it's not the why, it's a consequence that the current is different. See? Okay, but it's 9.8 in both places. So I think you're onto something, but you have to say it better.
The submerging would limit how big the weld can be?
You say the fluxes?
Yeah.
How would they limit it?
Well, it would restrict you to the area that you're welding in at that point, whereas with EGW, you've got more freedom of where you're working.
You're onto something, but the fluxes, although it's true that the fluxes sometimes help us to keep the weld in place, they are not the limit in this case. Because if I put the current of electrogas welding, I melt everything. I can't. So, but you're are onto something. You guys are approaching it. So this is the deal. In electrogas welding, I have a swimming pool of molten metal. But I can have a swimming pool of molten metal because I have the two plates that are super thick on two edges and the copper shoes on the other edges. In subarc welding, you don't have copper shoes. So if you're going to dump a bucket of molten metal, it's just going to flow. That's your limit. And what prevents it from flowing? Surface tension, capillary forces, right? With a little bit of help of the flux. But it's not too much, right? So that's the reason this is bigger, right? Now, if capillary forces are my limit in subarc welding, and they are my limit for MIG, why is this bigger than MIG? You will see the machines in the lab, and we'll demo those, and you'll do MIG by hand, right? So something you will learn formulas about this, but if I make a small weld, has a small, the welds look like comets. You will see that yourselves. They look like comets, right? You have the torch here, and as you move, it has like this hot tail behind. So if I have MIG, I have gas shielding, and I protect the tail. If I make a huge weld, it's going to have a huge tail, right? You know this from intuition. We'll give you formulas for that, but typically, big weld, big tail. You cannot shield it with the gas, right? But with the fluxes, you have all this layer of molten flux, right, or solid flux protecting from the atmosphere, right? For that reason, you can make enormous things. If you wanted, as indeed happened in my PhD or the PhD of one of my students in the US, you say, I want to use, in my case was TIG, make huge TIG welds. Yeah, sure, but TIG has this little shielding area, and when the tail starts trailing behind that shielding gas, starts getting a look of Swiss cheese. Not good. You don't want anything done with that. So I'm telling you these things as preparing the ground, because we will study. I'll give you the formulas to calculate the length of the tail, right? And you'll start understanding and making sense of many things yourselves. So typically is mechanized and in the flat position. Okay, why would it be in the flat position? Yeah, the powders. You do it overhead, right? Never goes well, right? Although you could, but then it becomes very difficult, right? You could start pushing the fluxes, playing games, or you can do it in position 2. Yes, you can. In welding, yes, you can do everything. You might not want to. Why mechanized? If you remember, mechanized means like you put on a gantry or something that moves. Why not manual?
It's really hard to see underneath the slag.
It's kind of hard to see, right? Like, yeah, you see nothing, right? So one of the funny things is the operator does not need to be a welder, and you don't need protection for the light because you don't see the arc. You'll see this in action. You typically do this in shops. However, now that you know, if you pay attention, you might see every once in a while those welding rigs. You see those pickup trucks that have the welding equipment. Here we have infinite of those in this province. Some of those have subarc welding. Not common. But those guys can do what nobody else can, right? You get a pickup truck and you say, what do you want me to weld? That bridge? Yeah. Right on. Right? So everything large and thick we can do. Shipbuildings, tanks. Remember when I told you the story about the T-34 tank, about the Soviets, 7-1? The Panzers were better, or maybe not, because the Russians could make more than 7-1, right? It's because it was subarc welded. So you will see that in subarc welding, you end up with all this slag here. So when they first demonstrated the welding of the T-34 to the Soviet powers to be, they do the weld, right? They take the powders out, and it looks horrible because they see all the slag. And they say, this is never going to work. And then the engineer comes, chip, 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 chips all the slag, and it's this beautiful, shiny weld. and the rest is history, right? Very interesting. Let me show you the video on subarc welding here. We're training videos. Oh, hold on. Wow, I'm having a special day today, huh? Okay. Thank you. Let's go. I don't want to see any iMovie.
Consumable.
There we go. There you go.
In submerged arc welding, a bare, continuous, consumable electrode
Fluxes.
wire.
This flame not always is there.
Layer of granular
It's just from the temperature and the burning of the ceramics.
the arc. When the arc is struck, the tip of the electrode is submerged in the flux, and the arc is not visible. Welding proceeds without the intense radiation that characterizes open arc processes, and with little fumes. The submerged arc welding process varies from semi-automatic to fully automatic.
No safety glasses, no
Automatic
jacket.
wire feed devices
Not good.
and joint tracking systems to move either the welding head or the workpiece. Submerged arc welding is commonly used to join all types of steel, stainless steels, and nickel alloys.
All right, awesome. So, steels, stainless, nickel. How about aluminum? It didn't say aluminum, so the answer is no aluminum. Why? I want the maths here.
Because it can be easily oxidized.
Exactly. Thank you. Thank you so much. Right? When you have these fluxes, there are these chemical reactions. Fluxes are typically oxides. Well, aluminum will steal the oxygen from everything except titanium. Right? So if you want to do subarc welding of aluminum, it's not going to work. All right, so you might say, how about if we try something that is not oxides? For example, fluorides. And we have tried this in the lab, right? And every few years, people come with their grand idea of subarc welding of aluminum. That would be amazing, so useful. But if you use fluoride, fluorides are very hygroscopic, right? So they absorb humidity, absorb moisture. And if you have moisture, then you have hydrogen, right? And hydrogen is very bad for aluminum too. It doesn't give you cracking like in steel, but gives you porosity, right? So subarc welding, which is super important, is essentially constrained to everything iron or nickel base, right? Because of the reactivity of the fluxes. Having said this, what do you think of flux core of aluminum? That doesn't happen either. That's another thing that every once in a while somebody comes with a bright idea. It's not happening, right? However, there are sticks. Well, when we get to stick welding, there is one flux-based process for aluminum, but it's so uncommon, so uncommon. All right, let me show you. This is from our lab. So this is a machine you'll see. You see, in our case, you see no flame. We didn't have a big flash to start. Okay, I should stop it here. Okay, that doesn't matter. That was part of an experiment. So, you see, we were doing something that I'm going to show you now. You saw that it was about to explode? Okay, that's why it looked like it was about to explode. So, subarc welding, right, is so similar to MIG. You have droplets that come from the electrode to the weld pool. Is that globular or is it spray? What is it? You have no idea because you can't have any idea. And nobody has an idea, but we do because we did these experiments in the lab. So I'm going to show you a video that is a super big deal because some people in Germany had done videos like this in 1960, when was that? It was 50 years ago. I think it was 1968, right? Or maybe earlier. And then nobody could do this again. But we did it. We had a guy coming from Germany, and in 1 week of working together, we did this. It's a major breakthrough. So I'm going to show you a video of metal transfer in submerged arc welding. This is just to whet your appetite, because in a metal transfer session lecture we're going to have, I'll show you much more. So metal transfer in submerged arc welding. So this is a droplet. This is a wire. This is 10,000 frames per second. So this has been slowed 10,000? 300 times. This is 300 times slower than reality. This is a droplet. You see the wire now is molten here. Here you have the arc. Here you have the weld pool. This kind of thing you see is part of the trick we did, in which we put like a little tunnel to see inside. And when you start to see the sparks flying in the video that I stopped it, it's because the sparks were coming out of that video. So now it's funny. To some extent, this would qualify almost like globular. You see the fluxes, the dry fluxes coming from the top. But you cannot compare this with globular transfer in MIG, right? In MIG was this beautiful big droplet, would go a little bit to the sides. But now this droplet is big, but it's not too beautiful. It looks like a horror movie type of amoeba monster, right? Like, so this is important because it informs us of many things. One is, how is the metal moving? Does the metal fall straight or makes a bank shot against the molten walls of the fluxes, right? We also get to see what is your arc length, because you can set the contact tip to workpiece distance. Do you remember what that is? From the contact tip to the plate. You do that. But once you turn on the arc, you don't know how that distance is divided between arc and electrode extension. But now we know, because we're measuring it, right? So we did so much scientific work with this. We got to learn so much. And then, not too far after we did this, some submerged arc welding machines started to come with waveforms. But to develop a waveform, you need to know what's happening to the droplet, right? And they wouldn't do it because they have no idea what's happening to the droplet. So I don't know how much use they put to our videos, because in industry they're very, very secretive. Let me tell you an interesting story about this. I visited Japan for a conference a couple of years ago. It was after we published this paper. And I'm happy in my conference in Tokyo, and they said, would you like to come see our company? Yeah, sure, why not? Like I say, okay, now they put me in a car where they kidnapped me. They take me to one place that was an hour and a half away from Tokyo. And they put me in front of this welding machine, right? A sub-arc welding machine. And they start asking me all kind of questions about this, right? This experiment. It was funny. I felt like being interrogated. But that means that somebody once cared about one thing we did in the lab, right? As an academic, that so seldom happened. So I was very happy. But this is a big deal you get to see here. All right, true or false? False. Like if you remember, like sub-arc welding is massive, right? It's a chainsaw. MIG is like a knife. Very, very different, although they're so similar. And again, like everything has an exception. If you wanted to do a submerged arc welding at 400 amps, yeah, you can do it with a MIG machine, right? It's not designed for that, so you have a few challenges, but not unsurmountable. Similarly, you can do gas metal arc welding with sub-arc welding, right? But again, the machine is not designed for that. You can make a gas nozzle, but it's never going to be as good. And if you say, well, but I wanted to do it at 1,000 amps, and I say, good luck with your shielding, because you're going to have this enormous tail, right, that you cannot shield with the gas. So things are there for a reason. So, sorry, I'm mangling. Carolyn? Was that Carolyn? OK. You said that we typically would do sub-arc welding mechanized because you don't see what you're doing. But for mechanization, you need some sort of equipment. This is the way they do it. They used to do it in the Soviet Union. Right? The guy is not watering the plants here. Huh? Here's the torch for sub-arc welding. Here's the groove. So all the guy needs to do is just keep a constant speed, right? And the head is running on the groove. So as you see, for everything I tell you, you can prove me wrong with one example. So I cannot give you a universal law for things. I can only talk about typical things. Here you have an exception. Isn't that cool? So you can do anything you want with welding. Yes, as long as you can pay for it. All right, electroslag welding. So now, electroslag is to electrogas what subarc welding is to MIG, right? So MIG, I melt a wire, cover with gas. That's same as electrogas. The difference is one is enormous and one is controlled. One is a swimming pool that 4 sides, and the other is controlled by capillary forces. Electroslag welding is the same as subarc welding, except it's massive. So you make this swimming pool of weld with 4 walls. Now, I wasn't completely true. There is one difference between electroslag welding and subarc welding that is important, and it's very important. You have fluxes. You have a slag, you have molten metal, you have the copper shoes. Same thing, you know. The fluxes are the same as subarc welding. However, an electroslag is classified as typically as a arc welding process, and that's why I put it here. Guess what? You have no arc. No arc. But you still run current. And it happens is that some fluxes, when they are very hot, they become electrically conductive. Right? So you run the electricity from your electrode to the molten metal, right? And you melt the wire, right? Just as you did with MIG or anything else. But you have no arc. So fluxes that would give you this type of performance are very high in fluorine, or fluorides, which are not oxides. Those are, I don't know what they're called, fluorides, right? So this is very interesting. There are limits to what I know about here. I will teach you lots about how to understand the voltage in arc welding. But for example, if you have a voltage near the electrode or a voltage near the plate, I still don't know that. But you're not forming an arc, so the whole process is very different, right? This is the biggest weld you can make. Right? This is the biggest weld you can make with the technologies that people handle. Right? In a single pass, I mean, in a single pass. You can weld enormous welds, making many, many passes with everything. But in this one, you get to do one in one pass. So protection of the melt is fluxes, not a gas. You have automatic wire feed, can be solid, can be metal core, and the polarity is typically electrode positive. Right? This is a common welding procedure for enormous things, much like when I mentioned before, things like ship bridge construction. This is not a weird process. This is used. So what else? All these things is mechanized, very high deposition rate. The operator does not need to be a welder, right? Same as I mentioned before, an operator is to a welder what the DJ is to the musician. How many of you are DJs here? You can raise your hand. Well, they have a thin skin when you say you don't play music, you play a button, right? I play music, I'm horrible though, so I should stick to playing buttons. Again, as you guys know by now, if you have a huge weld, it's a huge amount of heat that takes very long to dissipate, will give you a huge heat-affected zone, very high heat input. All right. Stick. When you go to welding school, the first thing they'll teach you is what I'm teaching you last, stick welding, right? And the reason I'm teaching it last is because actually it's relatively easy to do by hand, but we need to have built many things to explain it, right? To some extent it's complex because you're melting an electrode, right? So it's a consumable electrode. It's more difficult. The physics is more difficult than TIG. You have fluxes, right? Like we had in flux core, right? You have the weld pool and all those things. But in addition to that, it runs. It's a stick, right? It's a rod of finite length. It's not like a spool that is not infinite, but looks like infinite because you keep on spooling, right? So this process is what you might have typically seen, and you will do this by hand yourself in the lab, right? They give you a stick, you put this, and then it's very difficult to make work, right? But once you get a hang of it, that will be good. When I was a little kid, my dad built 2 campers, and he taught welding himself, and he taught me some. So I thought I was so awesome. I could go some of that. But I should not weld anything that goes under pressure, that for sure. What do we have here? We have the arc, weld pool, the weld, the slag, right? Here we have what they call the rod, right? This is the rod, and here we have the coating, right? This is the electrode, but these are the fluxes. This is the coating. So people call it also coated electrodes, right? Because although you have this steel rod, you see only the tail of the steel rod. You see the fluxes. This is among the oldest welding processes, right? People started to use carbon rods, like TIG, right? But instead of TIG, we were using a carbon rod. Okay, go somewhere. Then they said, okay, how about if we use a piece of wire? Okay, or a piece of, a steel rod. And it would look like Swiss cheese, right? But at least they would get the 2 things together, right? I'm talking about like 150 years ago, right? Or 100 years ago, right? And then someone, and this is one of those funny things, they realized that if the electrode was rusty, it welded better. And then they started to do something crazy. They started to wrap these electrodes in newspaper, and they were super good, right? Newspaper, do you know what the key ingredient of newspaper is? Not news, the other side of the paper. Newspaper paper is wood, cellulose, right? And you might have heard about cellulosic electrodes. Well, that's the same thing they were doing 100 years ago. Now instead of wrapping the newspaper, you chop the newspaper before you put it. But it's the same thing, right? And we'll talk about why that was good and how it worked. So very old technology. You saw this photo in the first class, right? Here we have the electrode. Here you have the arc. Here you have the weld pool. Could this be TIG? Well, it could not be TIG because you see this enormous arc, and TIG typically is sharp. You will see that. I don't remember, but we might be seeing that today, right? And if not next week, for sure, right? Could this be MIG? No, it cannot be MIG because in MIG the wire comes perpendicular, right? Or in stick you come at an angle. It's very different. Okay. So protection of the melt in these cases with the fluxes. Remember I mentioned this word basicity before. That has nothing to do with pH, and it's not even all too scientific. But people have this general, it's called a heuristic, like rule of thumb, that if you have basicity, and I'll tell you what it is depending on the type of oxides you have, you're going to have higher or lower oxygen. When it's cellulosic, right, you have higher penetration. Nobody understands exactly why, but the cellulosic have what they call a very stiff arc. I believe it's because the arc of hydrogen is an arc that is quite constricted. But for that, we need to do more work on the science of plasmas, right? But if it has penetration, then people use it for things when you need to go deep. The filler metal is rods, not wire. Now you can imagine you're welding like we do in the province, in which we use this a lot. This is the standard for using this province. Let's say I wanted to weld something on this edge, and I come with my stick. Oh, I ran out of stick. All right? shake the tail, which means waste and environmental problems, get another electrode. Oh, wait, the end is never too good, so I have to grind it. All right, now I come again. Oh, I ran out of electrode again. Okay, grind, toss, horrible. For this process, you're going to see we have a lecture on efficiencies. When you do a root pass, remember the root pass with these cellulosic electrodes? You put so much metal in, right? And then after you did your weld for the root pass, you weighed it after. What is your efficiency? If you have, say, 10 pounds of metal, right? How much of that ends up in your weld? A number. I'm sure it's not going to be 100 because nothing is 100. Maybe 10?
45?
Can be 0. I'll make it better. Can be negative. Actually, people have measured it's negative. Now you can say, how can it be you put metal and you end up with less metal? Because of the grinding. So you put the electrode, and then you have to grind it. And you put the electrode, and people have measured that in this province. And for a root pass, you can end up with less metal than what you had at the beginning. Still, you made your root pass. It's just you just ground all around the groove and everything. Isn't that funny, right? When I first heard this, I said, like, how can this be? Right. Now, tell me, if your productivity is negative, are you going to go too far in the world market? Well, the future is in your hands, all right? Like, don't do this. But this is what we do, and there are good reasons why we do this. But there are even better reasons to move away. So the polarity is typically constant current for reasons similar to TIG, right? You want an arc to be of constant strength. And in MIG, you keep feeding the wire because it's consumable, but you feed it automatically. In this case, you feed it by hand, so you're fine. Typically constant current. The polarity can be positive, can be negative, depends on the flux system, and we'll discuss this when we discuss plasmas. Typically, I've never seen waveforms for stick electrode, right? You can also have AC. And in this case, it's interesting. AC, the current that comes out of the wall is AC, right? So the cheapest welding machine you can do, that is what my dad had, guess what it is? A transformer, right? You don't want 110 or 220 volts. You want 20 volts or 25 volts. But you want 100 amps, right? So you have a transformer. Now, because you guys haven't had much of electrical engineering, transformers only work on AC, right? Transformers don't work on DC. That's why Tesla was successful where Edison wasn't. Edison was working in DC, and he couldn't transport electricity at long distances. Tesla would make transformers, increase the voltage, lower the current, fine. Transformers work on AC. If you work on AC, you are going to be positive sometimes, negative sometimes. You're going to be 0 sometimes. We're going to discuss. When you go through 0, it's kind of hard to maintain the arc at 0 current, right? So all these things come to play roles and result in commercial products. Characteristics. Well, stick welding is super versatile. This is only manual, but again, there are exceptions. I've seen it in a shipyard in Japan. They make these huge rods that you could not possibly use by hand. They put it in a slider, so as the rod is burning, like it keeps moving by itself, right? So everything has an exception, but here in this province, typically we do it manual. The skills to do this are higher than MIG, but lower than TIG. TIG is the most difficult. MIG is the easiest. Stick is medium. The deposition rate is low. This is not a very productive process. Now, there's a difference. TIG is not very productive because you're with a scalpel. This is not very productive because you have to stop, grind, right? Get the other electrode, put in the clamp, do it. Welders, like in the pipeline industry, they're a little bit like surgeons. The guy is welding, and right next to the guy, there's another guy with a bucket of electrodes just waiting to give it to him. In 2008, when I got this job here, our economy was flying super high. At McDonald's, you could not find anybody older than 15 because anybody who was older than 15 was holding a bucket of electrodes for $100,000 a year, right? We don't have that problem anymore. So, but it's not very productive. Cannot make too small details. You can end up with high hydrogen, for example, in these cellulosic electrodes. Cellulose, right, is an organic material. Carbon, oxygen, nitrogen, hydrogen, right? And the hydrogen is a problem. The equipment is super cheap. It's just a transformer. It does not get any cheaper than that. Applications. Outdoors, for sure, right? Because now my protection is a fluxes. Everything that is a one-off, we're good. Field welding, repair of pipelines, pools. Civil construction. If you're going to be climbing to the floor number 100 in a tall steel building, do you prefer to have your stick electrode, or you prefer to carry a tank of argon and all those things, right? Of course, the guys go with the stick electrode and get done, right? There are good reasons to use this. So don't get me wrong. It's not that this is bad. It's bad when you use it, but instead you should be using something else. And that depends on awareness. Are you guys fine? All right. Oh, here is our training video.
Shielded metal arc welding uses a covered electrode consisting of a core wire surrounded by a concentric covering, which is a mixture of silicate binders and powders. These binders and powders serve as a source of arc stabilizers, fluxing agents, lubricants, gases to displace air, and metal and slag to protect, support, and insulate the hot weld metal during welding. The bare section of the electrode is clamped in a holder, which is connected by a welding lead or cable to a terminal of a constant current power source. The workpiece is connected to the other power source terminal. Touching the tip of the electrode against the workpiece and withdrawing it slightly initiates or strikes the arc. The heat of the arc melts the base metal in the immediate area, as well as the electrode core wire and covering. The molten base metal, core wire, and metal powders in the covering coalesce or fuse to form the weld. The equipment required for shielded metal arc welding includes either an alternating current, or AC, or direct current, or DC power source, welding leads, an electrode holder, welding helmet and gloves, and protective clothing. The process is effective for welding ferrous metals such as cast iron, carbon, low alloy, stainless, and tool steels, and non-ferrous metals including copper, nickel, aluminum, and their alloys.
Let me tell you about aluminum. I talked with the person who developed the aluminum stick electrodes, right? And those are heavy in fluorides, right? We said we don't want to use oxides. They are a nightmare because fluoride is not all that different than, for example, a chloride. Like sodium chloride, like table salt, right? Have you ever seen like the salt, how it cocks in your salt shaker sometimes, right? That means it absorbs lots of moisture, right? So there are stick electrodes for aluminum. If you can use MIG or TIG, you'll be a lot happier. Sometimes you gotta do what you gotta do. Did you see when they show how you start the electrode? Okay, some people, the joke is, that's why it's called stick electrode. Let me show you. This is in our lab. Go. That's a stick electrode, right? So you got to see how it sometimes gets stuck? Okay. Don't laugh too much now, because then you'll see when you try yourself. It's quite tricky. It's quite tricky. But once you master it, it's exhilarating because you can start putting things together, right? You start becoming like having your very own industrial revolution, and then you go to Home Depot and you spend a couple $100, you get your own welder. Yeah. You can do everything. It's awesome. So, say, yeah.
If you use the stick electrode, does it give the same like strength compared to the other method you were explaining?
The other procedure. Okay. The question is if the stick electrode would give us the same strength. So many important things to bring up here.
Again, does it have, which one is more likely to have defects?
Okay. Two questions. One, you asked us about strength, right? So the answer is yes. But strength is the easy part. Making something strong is very easy. It might not seem like so obvious, but making something strong is easy. You want it strong and tough. That's difficult. Glass is very strong. I would not make a pressure vessel out of glass because it's fragile and it could burst, right? So
I'm not talking about the strength as in...
You're talking about mechanical properties.
Quality.
Right, mechanical properties. So mechanical properties depend on the alloy, and they are very loosely related to the process. So with every process, you can do pretty much all strengths. From the point of view of quality, right, depends. Quality in welding is defined as fit for service. So in some cases, spatter doesn't matter. Some other case, for example, if you're doing something you're never going to see, people don't clean the spatter. If you're making in the automotive industry, you don't want to buy a car that has all those spots, right? So although quality is defined relative to the different applications, overall, you're going to have processes that have less spatter, less porosity, less contamination with TIG. TIG is very high purity. Then MIG is good. Then sub-arc is good. Then you have flux core, like in the possibility of having defect. And then comes this. And this has all the problems of flux core, but in addition has the problems of starts and stops, right? So stick, when you weld stick and you want something high quality, yes, you can get it high quality, but it comes at the cost of lots of grinding, for example. So much grinding that sometimes the efficiency is negative, right? So does that answer your question? Yeah. But overall, everything can be, there's no process here that I would say this is a bad process. But I am saying that sometimes you have a choice between two processes. And if you choose one that, in the choice between the two processes, one might be clearly better than the other. When we use stick instead of flux core, often we're missing out, for example. Yeah.
Like maybe this one is more handy, like you can apply it on site. Like maybe like high-rise building.
This is super handy, super practical. Yeah. And again, you go to Home Depot and you don't even need to put the pin on your credit card. You just tap and you came up with a welder and a bucket of electrodes. Make machine is going to cost you more, right? So those are the decisions. What do you want, right? Yeah. So look, 6010 is one type of electrode of which you're going to learn everything. It's a cellulosic electrode. And I'm showing you two videos. We're welding a pipe from outside and from inside. So this is the a V groove, right? The V groove of a pipe. This is the edge of the electrode. This is at how many frames? 10,000 frames per second, right? These are the fluxes. This here is the metal being molten. And it's falling on the weld pool, and this is the weld pool. Do you see it? Okay, this is more difficult. Now, this is the same weld, or the same type of weld, but we put the camera looking from inside the pipe, right? So the weld is done close to the edge. Remember the position 6G when we talked about the welders qualifying? And I had a photo in which the guy was welding something that was relatively short, right? So that's what we were doing. So what we see here is from the inside, this is the weld pool, but the weld pool has been poked. They call it a keyhole. right, which has nothing to do with laser welding or electron beam welding. And remember that I mentioned the cellulosic electrodes have a strong arc, what they say a stiff arc. It just pokes through here. And this thing you see here, these are the fluxes of the coating of the electrode. And this is the molten metal that is being transferred to the weld pool. Right? In this case, they are doing a root pass of a pipe. Right? And 6010, which is a strong arc, they use it to make sure they melt the bevels, the root of the joint preparation, right? So they would not have a problem of lack of fusion. So here you're seeing weld, essentially you're seeing weld from below. All right. True or false?
False.
False, horrible, right? False, super false. Really low productivity. You still might want to use it, but don't be fooled, right? Strip cladding. So we have some rolls of this in the lab that if you're curious, we can show you. You see this drawing? This looks very much like subarc welding, right? And it says subarc welding. But there is a difference that is not clear in this drawing. This thing here is not the wire. It's a strip, right? It's like a sheet of metal that comes down. And what is the advantage of this? Well, instead of making like one line, you're making like one wide track. So sometimes you want to put two things together, and you go with a line of molten metal that puts them together. But sometimes you want to cover your metal the way you would put butter on a toast, right? That would be called coating or cladding or overlays. You do that for wear protection. You do that for corrosion protection, right? If I'm doing subarc welding, right? It's like painting a line with a brush. But if I do strip cladding, it's pretty much the same, but I'm coming with a roller, right? You go with this wide track, roller, much wider, much more productive for doing cladding, right? For overlays. Here it says electroslag welding. I just mentioned electroslag to you. And in this case, we don't have copper shoes. We don't have any of those things. The reason they call it electroslag welding is because it's much the same as this subarc welding, but there is a difference. Do you remember the main difference in the physics of electroslag welding with the other arc welding processes?
There's no arc.
There's no arc. Although we classified with arc welding, there's no arc. So they use these special fluxes. In this case, they say, OK, let's put the fluxes only here in the front. And of course, if you don't put fluxes here in the back, all this part would expose the molten metal. But in this case, you melt the fluxes, you don't have an arc, and the current just goes through here, depositing the clad, right? Electroslag. So these would be fluxes with very high fluorides. You use both, and they're good for cladding. There is something when you're talking about cladding, right? Imagine I'm putting chromium carbide overlay, right? I'm paying for chromium, which is very expensive, and as I put it over the steel, I need to melt a minimum of steel, otherwise it doesn't stick. But if I melt too much steel, then I'm diluting my chromium, for which I paid dearly. Not good. So this dilution, right, is marked here, right? And you, although there are formulas for this, you intuitively know that if you're going to melt a lot of the base metal, you're going to have lots of dilution, right? And you want low dilution. So the advantage of electroslag welding is that the dilution is lower than in submerged arc welding, right? And one of the reasons you're going to see this is because in submerged arc welding, the plasma arc puts a lot of heat here on the plate, while in electroslag welding, it puts much less heat because you don't have an arc and the problems of the arc. So strip cladding, the protection of the melt is fluxes. The filler metal is a strip. You see, these are the rolls. This is not wire. These are the strips, right? Polarity, typically electrode positive, right? Can make wide passes. typically mechanized, right? And of this one, I never heard of doing it any way that is not mechanized. Much the same things as subarc welding. The dilution is low. Subarc welding with a wire gives you high dilution, right? So what this strip is very wide. Sometimes the current is actually not divided evenly over the strip. The current goes like a zigzag, like you have these points of current. Whatever is closer is what keeps the arc. And then once you consume all this, it comes back and comes back and comes back. At the very edges, you have this pinch force that can cause an undercut. And this is a word I didn't mention. It's the first time I use in this class. Undercut is this. Imagine I have a plate. This is a cross-section of my weld, right? This thing here, right? Ideally, you want it to be like this, right? The toe should be right on the surface, but sometimes it's under. This is called undercut. People also call it, when they do this same problem with 6010 electrode, they call it the wagon tracks. Like the wagon tracks here. And of course, when they come and grind all of this, right, that's how you end up with negative efficiency. This is a shop welding operation, applications, wear and corrosion protection. In the petrochemical industry, we do it much. This competes with explosive bonding, and I will show you explosive bonding in the next slides. So this is for arc welding processes with fluxes. Do you guys have any questions or comments on it? As you see, welding is a whole world. We used to have a class only of processes, but we're going to do so much more than that. I want to show you solid state processes because we're going to be demoing those soon. All right, so when we talked about classification of joining processes, we said permanent and not permanent, right? Not permanent would be bolting. If it is permanent, it's because there was rapprochement of the atoms, right? And the rapprochement meant the atoms would share would have a chemical bond, so they would start sharing electrons. That could happen in two main ways. One is you heat it up so much that it melts, and then the melt, everything is molten and goes solid and became one. Or the other, it doesn't melt, but in solid state, you hammer it, you put enough pressure and temperature until the rapprochement happen because you beat it to death, right? So we have been talking so far only about fusion type of processes. I want to make a parenthesis. I'll pick up on fusion processes again, but because we will show you some of these solid state processes, I want to show you now. So this is rapprochement by fusion. One is friction stir welding. We have a machine. We're planning on running it for you to see. This is the way you weld rockets. Right? This is the way you weld the deck in some, the aluminum deck in military ships or ferries. Or this is the way you weld trains in Japan, the high-speed trains in Japan. So this is a big deal. And this is a process that was invented in the 80s. It's the newest mainstream welding process. Right? People invented the MIG and TIG and electron beam, and then nothing happened for a good while. Then friction stir welding. And then there hasn't been a breakthrough again. So in this case, you have this is, they call it an anvil. This is essentially like a very strong, stiff support. Then you put your plate typically is aluminum, but can be many other things. Typically aluminum. And then this thing here is a circular tool that is rotating, right? And actually, the tool looks like very much like a, well, in many cases, the tool is exactly a metric thread screw. Metric thread screw, right? So this is the screw, and this is where the screw is coming out. This part is called the shoulder, and this is called the pin, right? But the pin is metric thread, the screw. There are many variations on this. You see, I put a little bit of a tilt angle here. So this thing is spinning. And guess what? This is something, when I first heard about this, I thought people were wrong. But it's true, and we have it in the lab. If everything goes right, you'll see it. If I spin my pin, right, in my, let's think of aluminum, something's going to get hot in there, right? Just the frictions of whatever reason is going to get hot. Now, it's going to be hot locally near the pin, and outside it's going to be cold. So if it is hot locally, means, and this is intuitive, it's also soft locally, right? Because hot metal has lower yield strength, right? So if it is soft locally and I'm spinning, the deformation is going to catch on, and it's going to be deformed locally, right? Now, because you guys know that if you deform metals, for example, by bending a paper clip, have you ever broken a paper clip by bending? You do that in Marito too. You have a question? You did it? You did it? Have you touched it? It gets hot, doesn't it?
I was told not to touch it, so I did.
You should have had taken my class. It is, you get to hear some good yelps there. So it gets hot. But of course, if you're making force and moving, you're putting energy, right? Force times distance is work. All that work, where did it go? In heating up that part and bending it, accumulating dislocations until it breaks. So now we have this localized deformation that generates localized heat. And the localized heat makes it locally soft. If it is locally soft, I have localized deformation, and there you go. So in the right conditions, which are not trivial, in the right conditions, this thing stirs. That's why it's called friction stir welding. Just the amount of metal around the pin, and as you translate, the metal is not melting, but it's coming together as if it was plasticine. This is amazing, right? And it works. First time I heard it, I said, no way. But it's true. So here you have the shoulder, because this metal is not molten, but it's very soft. We'll want to squirt out, right? But you pin it with the shoulder against this anvil, right? And you go. So in this case, because there is no melt, you don't need protection. First happy thing. You don't, filler metal. This is autogenous, right? I have no filler metal. People are trying to do all this kind of crazy stuff, but for the most part, no filler metal. It's autogenous. The mechanical motion is rotation and translation, right? And when you see a cross-section, it looks very different than a fusion weld, because you have the parent metal here, the base metal, have a heat-affected zone. By in addition of a heat-affected zone, you have a thermomechanically affected zone. That's new, because when you melt things, you don't have thermomechanical actions, right? And they call the weld nugget here where it was moving. Why this is not symmetric? Well, when you're spinning and moving, one side is called the advancing side, it spins in the direction of motion, and the other spins back, right? So that gives you an asymmetry. That's not a problem. So this type of process, you imagine, I keep mentioning aluminum because I can use a steel tool. Because steel, the aluminum gets hot, but the steel is still going to, hot and soft, the steel is still going to be strong. Now, what do I use for steel? Not trivial, right? You can use tungsten, you can use ceramics, but steel is a big nightmare. Has been done, can be done, is not frequently done. These can weld unweldable alloys. So something called weldability it means can I weld it or cannot? So really, weldability doesn't mean anything too concrete. But you say, can I weld it or cannot? Very often, the answer is no, you cannot weld it. And it's because some alloys, when they go liquid, right, then they want to solidify. And because all of you took MATI 202, you know that when you go from solid to liquid, you have to go according to a phase diagram. And the phase diagram says that the solid will have a composition, but the liquid a different composition, right? Typically, you end up rejecting solute. That means if you have an aluminum copper alloy, like 6061, has 4% copper, what goes solid is pretty much pure aluminum, but your liquid is rich in copper. So the next bit gets solid, is pure aluminum and richer and richer in copper. So in the end, you have something that is super rich in copper that ends up also, if you remember the term eutectic, right, ends up causing all these problems. It curdles like milk, right? And you say, this is unweldable. Well, no, it's not unweldable. It's unweldable the way you're doing it. So people, by doing this, can weld all these unweldable alloys. This is an awesome story. To build the space, the space shuttle has this huge orange tank, right? So the great minds realized that if you mix the aluminum with lithium is a very light metal, it's going to make a light alloy, lighter than the aluminum, and you would save, I don't remember how many hundreds or thousands of pounds. Everything you save in your tank is something you can put inside the space shuttle. That's awesome. What a great idea. Let's make these tanks, right? Well, you cannot weld them. You cannot weld them because you have all these issues of that end up resulting in cracking, hot cracking during welding. So the problem had two stages of solution. One is, how about if you make a tiny weld, right? A very narrow weld. And here in Canada, people developed a process called variable polarity arc welding, VPPA, that could do it, could just do it. The Chinese used that same process to weld their space station, for example. But then there is a second stage of development that was friction stir welding. Right today, most rockets are, with the body and the tanks of most rockets are welded with friction stir welding, right? This is pretty cool. It was an enabling technology. Now, you can, because it's a solid state process, you don't have problems with gravity because there's no liquid that is going to fall on you. But you have problems that you cannot do it manually because it's enormous forces, so you need a strong anvil and a strong machine. And you're going to see the machine we have in the lab. It's an enormous converted milling machine, super heavy, right? It's also, as I was talking about the thing steering, you realize that you cannot have a gap. If you have too big of a gap, right, as you stir the things, you're going to create a mess with porosity because you're missing metal there, right? It's autogenous. In autogenous welding, you typically want no gap. Because if you have a gap, guess what? There is no filling to make up for it. Sometimes you can, instead of like doing this and moving, you can go in and out. This is called friction stir spot welding, and it's used in the automotive industry. Not widely used, but it is used, especially when you have aluminum components or you want to mix aluminum and steel or aluminum magnesium. This friction stir spot welding has been used in automotive. Applications, shop welding. This is not a field welding type of thing. Typically, this is full penetration, right? Butt joints in aluminum rocket body shape, the things I mentioned to you. I'll show you one video here, and then we'll stop. This is a video of friction stir welding. We didn't make this one, but so this is rotating. It doesn't look like, but it's rotating. So it's doing what is called plunging. Right, you're going to see it goes down. There you go. Goes down and will start moving. So this is a video from some university. We should make our own. There's a little bit of a burr, right, that you have to clean up later. But you see, this is all clean, all together. So let's stop here because we're going to one of to our to the Thursday. Yeah, we're going to the lab.